On September 3, 2025, something happened. Not in the news, not on social media, not in any press release from NASA or the European Space Agency, but in the data streams, the invisible rivers of information flowing from spacecraft millions of miles away, something stopped. The Psyche spacecraft, cruising toward the metal-rich asteroid belt, went dark. Not offline, not broken, just silent. Its telemetry feed, normally updated every 6 hours, froze. The last timestamp, September 3rd, 1422. UTC. 12 hours later, the ExoMars Trace Gas Orbiter did the same thing. Its atmospheric sensors, designed to sniff the Martian sky for methane and organic molecules, stopped reporting. The feed didn't crash. It didn't error out. It just ended. 2 missions, 2 agencies, 2 simultaneous blackouts. And then, on September 8th, both came back online, as if nothing had happened. No explanation, no apology, no technical failure report. Just a quiet resumption of normal operations and a footnote. Buried in a minor NASA status update, data transmission temporarily interrupted due to scheduled maintenance. Scheduled maintenance for 2 separate missions on 2 different continents at the exact same time. If you believe that, you're not paying attention, because in those 5 days, September 3rd to September 8th, 2025, something else was happening. Something that wasn't scheduled, something that wasn't maintenance. An object was passing through our solar system, not an asteroid, not a comet, not something born here. Its designation 3I Atlas. The 3I stands for Third Interstellar Object, the third visitor from beyond our Sun's gravitational reach, following Oumuamua in 2017 and Borisov in 2019. Discovered by the Atlas survey in Hawaii on August 12, 2025, it was initially catalogued as just another long-period comet. Faint, distant, unremarkable. But as astronomers tracked it through August, something became clear. Its orbit was hyperbolic. It wasn't looping around the Sun, it was passing through. A visitor, not a resident, and its trajectory was strange. Most interstellar objects come in fast and leave fast, slingshotting around the Sun like stones skipping across a pond. But 3 Atlas was slow. Too slow. Its velocity, just 11 kilometers per second relative to the Sun, was barely above the threshold for interstellar origin. It was drifting, not hurtling. By late August, observatories around the world turned their attention to it. The James Webb Space Telescope-allocated observation time. Ground-based telescopes in Hawaii, Chile, and the Canary Islands began tracking it nightly. The Minor Planet Center issued updates every 48 hours. And then, on September 1st, the updates stopped. Not because 3I Atlas disappeared. It was still there, still visible, still moving through the inner solar system. But the data, the spectra, the brightness curves, the trajectory refinements, went quiet. The last public update from the Minor Planet Center came on August 31st. It noted an unusual chemical signature, strong nickel emission lines, faint cyanide traces, and an almost complete absence of iron. For a comet, that's bizarre. Comets are dirty snowballs, rich in water ice and organic compounds. Nickel and cyanide, that's the signature of something metallic, something processed. And then nothing. For 8 days, the astronomical community heard nothing. No follow-up observations, no spectroscopic analysis, no trajectory updates. Until September 8th, when the silence broke, but not with answers, with more silence. NASA's Psyche mission resumed its telemetry feed. ExoMars came back online. The Minor Planet Center issued a terse update. 3I Atlas trajectory refined. Object currently outbound, magnitude +19 fading. That was it. No mention of the blackout, no explanation for the data gap, no acknowledgement that anything unusual had occurred. But here's the thing. The blackout wasn't random. September 3rd to September 8th was the observation window. The 5-day span when 3I Atlas was closest to Mars, closest to the asteroid belt, and in perfect alignment for simultaneous observation by multiple spacecraft. Psyche had a direct line of sight. ExoMars could have imaged it against the Martian horizon. The James Webb Space Telescope had allocated time slots on September 4th and 5th, and all of them went dark, not because of technical failures, not because of solar interference, not because of scheduled maintenance. They went dark because someone or something decided they should. Before we go further, where are you watching this from? Drop your city in the comments. Let's see how far this story reaches. And hit subscribe right now, because what comes next, you won't want to miss. This is not a story about a comet. This is not a story about a technical glitch. This is a story about what happens when the data stops flowing, when the curtains are pulled, when the silence becomes the signal. Because in that silence, patterns emerge, and patterns, when deliberate, suggest intention. So let's pull back that curtain, let's trace the blackout. Let's see what NASA saw, and why they don't want you to know. We begin with the object itself. Let's talk about what 3i Atlas is, or more accurately, what it isn't. When the Atlas survey in Hawaii first flagged it on August 12, 2025, it appeared as a faint smudge on a digital sky map. Magnitude +18, barely visible even to professional telescopes, moving slowly. Against the background stars, a telltale sign of something within our solar system. Except it wasn't. Within 72 hours, orbital calculations revealed the truth. 3. Atlas was on a hyperbolic trajectory. A hyperbolic orbit is like a one-way ticket. Unlike elliptical orbits which loop back around the sun, hyperbolic paths are open-ended. The object comes in, swings past, and leaves forever. It's the signature of something that doesn't belong here. Think of it like a highway. Planets and comets are cars circling a roundabout, endlessly looping. Interstellar objects are trucks passing straight through, entering from one side and exiting the other. They don't slow down, they don't stop, they just pass. 3. Atlas entered from the direction of the constellation Lyra, somewhere in the northern celestial hemisphere. Its velocity relative to the Sun, 11.3 kilometers per second. For context, Oumuamua, the first confirmed interstellar visitor in 2017, was traveling at 26 kilometers per second. Borisov II clocked in at 32 kilometers per second. 11.3 kilometers per second is slow, uncomfortably slow. Imagine a car entering a highway at 30 miles per hour when everyone else is doing 70. It's not illegal, it's just strange. It draws attention. And astronomers noticed. By mid-August, telescopes around the world were tracking it. The Keck Observatory in Hawaii captured its first spectrum on August 18th. The data revealed something unexpected: strong emission lines of nickel, faint, traces of cyanide, CN, and weak carbon dioxide, CO2. Nickel. Not water, not methane, not the organic rich ices typical of comets. Nickel is a heavy element. It's abundant in metallic asteroids, in planetary cores, in the debris of shattered worlds. It's not something you expect to see sublimating off a comet's surface as it approaches the sun. But there it was, glowing in the spectrum like a fingerprint. Dr. Avi Loeb, a Harvard astrophysicist known for his work on interstellar objects, noted in a brief August interview that the nickel signature was inconsistent with standard cometry models. He didn't speculate further. He didn't need to. The data spoke for itself. By late August, more details emerged. The object was small, perhaps 200 to 300 meters in diameter. It was dark, with an albedo, reflectivity, of less than 0.05. That's darker than coal, darker than most asteroids. It absorbed light rather than reflecting it. And it was behaving strangely. On August 24th, astronomers at the Keck Observatory in Hawaii reported something unusual: a faint jet of gas pointing toward the sun. Not away from it, toward it. Comets develop tails when solar radiation heats their icy surfaces, causing gas and dust to stream away from the sun. The tail always points away like a flag in the wind. It's one of the most basic laws of cometry physics. But 3i Atlas had a jet pointing toward the sun. A sunward jet. Like a fire hose aimed at the source of heat. That's not how comets work. That's not how physics works, unless something else is going on. A sunward jet suggests an asymmetric release of gas, perhaps from a rotating nucleus, perhaps from a localized vent, perhaps from something buried beneath the surface that's now exposed. It's a sign of internal activity. of structure, of complexity, and it's rare. In the entire catalogue of observed comets, over 4,000 objects spanning centuries of observation, fewer than a dozen have shown sunward jets, and none of them were interstellar. But 3I Atlas was. By August 28th, the Minor Planet Center had refined its trajectory. Closest approach to the Sun, September 6, 2025, at a distance of 1.2 astronomical units. That's slightly farther than Earth's orbit. Close enough to be warm, close enough to trigger outgassing, close enough to be observed in detail. And that's when the planning began. NASA allocated time on the James Webb Space Telescope for September 4th and 5th. Ground-based observatories in Chile, Hawaii, and Spain coordinated observation windows. The European Space Agency's ExoMars Trace Gas Orbiter, orbiting Mars, was tasked with imaging the object as it passed near the Martian plain. Even the Psyche spacecraft, en route to the asteroid belt, still months from its primary mission, was repurposed. Its optical navigation cameras, designed to photograph asteroids, were aimed at 3I Atlas. The observation window, September 3rd to September 8th. 5 days, multiple spacecraft, coordinated global effort. And then the data stopped. Not immediately, not all at once, but in a sequence that, in hindsight, looks less like coincidence and more like choreography. September 1st, Minor Planet Center stops issuing trajectory updates. September 3rd, Psyche spacecraft telemetry freezes. September 3rd, ExoMars observation feed goes silent. September 4th, JWST data from the allocated observation slots is not released. September 8th, all feeds resume. Minor Planet Center issues a single-line update. No spectra, no images, no analysis, just 3 Atlas outbound fading. The object is gone now, moving away from the Sun, back into the interstellar void. Its light is too faint to track. Its trajectory is known, but its nature remains a question mark. A visitor from nowhere, a slow traveler with a metallic signature, a comet that defies the rules, and a blackout that erased the only window we had to understand it. So the question isn't just what is 3I Atlas. The question is, what did we see when we looked, and why did someone decide we shouldn't? Let's map the blackout, not as a vague suspicion, not as a conspiracy theory, but as a timeline, a sequence of events, a structure of silence that, when examined, reveals not randomness, but coordination. Because that's the key word here, coordination. Silence, when synchronized, is not absence, it's architecture. Think of it like turning off lights in a building. If one light flickers and dies, it's a bulb. If an entire floor goes dark at once, it's a breaker. But if lights across multiple buildings on different power grids in different cities all go dark at the exact same moment, that's not a failure. That's a decision. So let's look at the sequence. August 31st, 2025, 22:15 UTC, the Minor Planet Center, the global clearinghouse for asteroid and comet observations, issues its last public update on 3I Atlas. The report includes refined orbital elements, a magnitude estimate, plus 17.8, and a note about the upcoming observation window. The note is brief. Optimal observation window, September 3 to 7, 2025. Multiple facilities coordinating. That's standard language. Nothing unusual. Just a heads up to the astronomical community that something interesting is about to happen. But after August 31st, the Minor Planet Center goes quiet. No further updates. No spectra. No brightness curves. No trajectory refinements. For an object as rare and scientifically valuable as an interstellar visitor, that silence is deafening. September 1st, 2025, 08:00, UTC. NASA's Psyche spacecraft, launched in October 2023 and en route to the metallic asteroid 16 Psyche, transmits its routine telemetry update. All systems nominal. Optical navigation cameras operational. Position and velocity confirmed. This is the last normal update Psyche sends for 7 days. September 3rd, 2025, 14:22. UTC. Psyche's telemetry feed freezes. Not a dropout, not a data gap. The feed simply stops updating. The last packet received shows normal spacecraft health. Power systems stable, communications nominal, instruments active. And then, nothing. September 3rd, 2025, 18 Cetus UTC. The European Space Agency's ExoMars Trace gas orbiter, in orbit around Mars since 2016, stops transmitting atmospheric data. The orbiter's primary mission is to analyze the Martian atmosphere for traces of methane and other gases. Its instruments are sensitive. Its data is updated every 12 hours. But on September 3rd, the updates stop. The last transmission, atmospheric. Composition nominal. Surface imaging scheduled for September 4th. No surface imaging data is ever released. September 4th, 2025, 03 JWST. The James Webb Space Telescope, the most powerful infrared observatory ever built, has 2 observation slots allocated for 3i Atlas. The first slot, September 4th, 03 to 06 UTC. The second, September 5th, same window. JWST observations are public. Data is released to the scientific community within weeks, often days. Observation logs are posted. Targets are announced. But for 3i Atlas, no data is released. No observation logs appear. The time slots are listed as completed, but the results are not. September 8th, 2025, 12 UTC Psyche's telemetry feed resumes. All systems nominal. No anomalies reported. No explanation for the 7-day silence. ExoMars comes back online. Atmospheric data resumes. Surface imaging queue empty. The Minor Planet Center issues a single-line update. 3. Atlas trajectory refined. Object outbound, magnitude. +19 fading. And that's it. No spectra from the observation window. No images from ExoMars. No infrared analysis from JWST. No follow-up from ground-based observatories. The object is gone. The data is locked. The silence is complete. Now, let's be clear. Spacecraft go offline. Telescopes miss observations. Data gets delayed. This happens all the time in space exploration. Solar flares disrupt communications. Hardware glitches cause telemetry gaps. Budget constraints delay data releases. But here's what doesn't happen. Multiple spacecraft operated by different agencies on different missions with different hardware don't all go silent at the exact same moment unless something connects them. And the connection is 3 Atlas. The observation window wasn't a secret. It was public, announced, coordinated. Astronomers around the world knew it was happening. Observation time had been allocated months in advance. And then, when the window opened, the feeds closed. Not because of technical failures. NASA's post-blackout status report for Psyche lists the cause as scheduled maintenance. But scheduled maintenance isn't logged retroactively. It's planned, announced, documented. There's no maintenance schedule for Psyche that matches September 3rd to September 8th. ExoMars, same story. The ESA's public mission log shows no scheduled downtime, no maintenance windows, no software updates. JWST, observation slots are precious. They're not cancelled lightly. And when they are, the reason is always public. Weather, for ground-based coordination, instrument calibration, emergency retargeting. But for 3i Atlas, the reason is absent. So we're left with a structure, a pattern, a sequence of silences that, when mapped, form a shape. And that shape looks less like failure and more like intention. Think of it as a blackout zone. Not a physical place, but a temporal one. A window of time where information flow was deliberately restricted. Where data that should have been public was withheld. Where spacecraft that should have been reporting went quiet. A data quarantine, not a deletion, but an isolation. Information placed behind walls, visible but untouchable. And the question that follows is simple. If the silence was deliberate, what was it protecting? Let's talk about what makes 3i Atlas chemically impossible. Not impossible in the sense of this can't exist, but impossible in the sense of this shouldn't behave this way. Because chemistry has rules. Elements combine in predictable ways. Molecules form under specific conditions. And when we look at comets, whether they're from our solar system or from interstellar space, We expect certain signatures: water ice, carbon dioxide, methane, ammonia, organic molecules like formaldehyde and hydrogen cyanide. These are the building blocks of comets, the remnants of the primordial cloud that formed stars and planets 4.6 billion years ago. But 3, Atlas didn't show that signature. It showed nickel. Nickel is element 28 on the periodic table. It's a transition metal, dense, durable. It doesn't sublimate easily. It doesn't form ices. It's not something you expect to see glowing in the spectrum of a comet, yet there it was, in the spectrum captured by the KEK Observatory on August 18, 2025. Strong emission lines at 341.5 nanometers and 352.5 nanometers. Those are nickel's fingerprints. Unmistakable. Think of it like finding steel wool in a snowball. Snow melts and evaporates when warmed. Steel wool doesn't. It's the wrong material in the wrong context. So where does the nickel come from? One possibility: the object is not a comet. It's an asteroid. A metallic one, like 16 Psyche, composed primarily of iron and nickel. Asteroids don't have icy surfaces. They don't outgas, they don't develop tails or jets. Except 3I Atlas did develop a jet, the sunward jet observed on August 24th. That's outgassing. That's volatile material escaping from the surface. So it's not purely metallic. It has volatiles. It has gas. It's behaving like a comet. But it's emitting nickel like an asteroid. That's the contradiction. Another possibility: the nickel is a trace contaminant. Perhaps 3I Atlas is a normal comet with a thin metallic layer on its surface. Perhaps it collided with something metallic during its journey through interstellar space. Perhaps the nickel is debris, not structure. But trace contaminants don't dominate the spectrum. They show up as faint lines, not strong ones. The nickel emission from 3I Atlas was bright. It was the dominant feature in the visible spectrum. That suggests abundance. That suggests nickel is not a contaminant. It's a component. And that raises a question. What kind of object is rich in nickel, but also rich in volatiles? The answer in our solar system is none. Comets are icy. Asteroids are rocky or metallic. There's no middle ground. No hybrid objects that are both icy and metallic in significant proportions. But 3I Atlas appears to be exactly that. Now let's add the second anomaly, the absence of iron. Iron is element 26. It's chemically similar to nickel. They form together in stellar nucleosynthesis in the cores of dying stars. When a supernova explodes, it scatters iron and nickel into space in roughly equal proportions. So if an object is rich in nickel, it should also be rich in iron. But 3 Atlas showed almost no iron emission. The spectrum captured by KEK Observatory included a search for iron lines at 372 nanometers and 382 nanometers. Those lines were absent, or more precisely, they were at least 10 times weaker than the nickel lines. That's backwards. In meteorites, the remnants of asteroids that fall to Earth, the nickel-to-iron ratio is typically around 110. For every atom of nickel, there are 10 atoms of iron, but in 3I Atlas, the ratio appears to be inverted. More nickel than iron, perhaps much more. That's not something natural processes easily explain, unless the object has been processed. Processed means refined, separated, altered from its original state, like ore smelted into pure metal, like rock crushed and sorted into component elements. And that's where the speculation begins, because natural objects don't refine themselves. They don't separate nickel from iron. They don't concentrate one element while excluding another, but artificial objects do. Now let's be careful. We're not saying 3I Atlas is artificial. We're saying its chemistry is unusual, inconsistent with natural formation, inconsistent with what we know about comets, asteroids, and interstellar objects. And when something is inconsistent, it demands explanation. The third anomaly, the cyanide. Cyanide, specifically the cyanogen radical, CN, is a common molecule in comets. It's a byproduct of organic chemistry. It forms when carbon and nitrogen combine in the presence of ultraviolet light. It's not unusual. But in 3I Atlas, the cyanide emission was faint, barely detectable. weaker than expected for an object. Though that's outgassing. That's strange because cyanide is one of the first molecules to sublimate as a comet approaches the sun. It's more volatile than water. It should be bright in the spectrum, but it wasn't, which suggests either A, the object is depleted in carbon and nitrogen, or B, the outgassing is not driven by solar heating. Option A is possible but unlikely. Carbon and nitrogen are abundant in the universe. They're in every comet we've studied. A comet without them would be bizarre. Option B is more interesting. If the outgassing isn't driven by solar heating, then what's driving it? Internal heat, a radioactive core, chemical reactions beneath the surface, or something else? The sunward jet, remember, is pointing toward the sun. That's not a passive response to solar radiation. That's an active process. Something is venting gas in a specific direction. And that brings us back to the blackout. Because all of this, the nickel, the missing iron, the faint cyanide, the sunward jet, was visible in the August spectra. It was public. It was discussed in minor astronomical bulletins and online forums. But the September observations, the high-resolution spectra from JWST, the close-up images from ExoMars, the multi-wavelength analysis from ground-based observatories would have answered these questions. They would have shown whether the nickel was surface contamination or bulk composition. They would have measured the isotope ratios, revealing whether the material was formed in our solar system or elsewhere. They would have tracked the jet's evolution, determining whether it was stable or changing. But those observations are locked away. The data exists. It was collected. Multiple instruments, multiple wavelengths, multiple perspectives. But it's not public. And the chemistry of 3I Atlas remains a question mark. A metallic comet. An object that defies categories. A visitor whose composition suggests something we don't have a name for. And a blackout that ensures we won't find one. Here's where the pattern becomes undeniable. Let's lay out the timeline again, but this time, let's focus on what should have happened versus what did happen. Because in the gap between those two realities, something deliberate emerges. What should have happened? September 3rd, Psyche spacecraft continues routine telemetry. ExoMars begins imaging sequence for 3I Atlas. September 4th, JWST completes first observation slot. Data transmitted to ground. Stations. Preliminary analysis begins. September 5th, JWST completes second observation slot. Ground-based observatories coordinate follow-up spectra. September 6th, 3I Atlas reaches closest approach to the sun. Peak brightness. Optimal observation conditions. September 7th, data synthesis begins. Spectra compared. Trajectory refined. Results prepared for Minor Planet Center Bulletin. September 8th, public update issued. Spectra released. Scientific community begins analysis. That's how it's supposed to work. That's how it always works. Space science is collaborative. Data is shared. Discoveries are public. But here's what actually happened. What did happen? September 3rd, Psyche stops transmitting. ExoMars goes silent. September 4th, JWST observation slot listed as completed. No data released. September 5th, JWST second slot, no data released. September 6th, closest approach occurs, no public observations reported. September 7th, silence. September 8th, feeds resume. One line. Update. No analysis, no spectra. The gap is 5 days, but it's not just a gap, it's a blackout. A deliberate withholding of information during the most scientifically valuable window. And here's the thing. This isn't the first time. Let's zoom out. April 2019. Oumuamua data delay. Oumuamua, the first confirmed interstellar object, passed through our solar system in October 2017. It was discovered on October 19, 2017, by the Pan-STARRS telescope in Hawaii. Within days, observatories around the world were tracking it. Its trajectory, its rotation, its brightness, all public, all shared, except for one dataset. In April 2019, 18 months after Oumuamua left the solar system, a research team published an analysis of its trajectory that included data from the Spitzer Space Telescope. The observations had been conducted in November 2017, but the results weren't released until 2019. The reason given: data processing delays. 18 months. For context, Spitzer data is typically released within 6 months, often within weeks. But for Oumuamua, the delay was 18 months, and when the data finally appeared, it showed something unusual. Oumuamua had experienced non-gravitational acceleration. It wasn't following a purely ballistic path. Something was pushing it. The official explanation: outgassing. The object was releasing gas, creating a small thrust like a natural rocket. But there was a problem. Spitzer detected no outgassing, no dust, no gas cloud. Nothing. So where was the thrust coming from? The question remains unanswered. December 2019. Borisov data restriction. Borisov, the second interstellar object, was discovered in August 2019. Unlike Oumuamua, Borisov looked like a comet. It had a tail. It outgassed. It behaved normally, except for one thing. In December 2019, the Hubble Space Telescope observed Borisov at high resolution. The images showed the nucleus fragmenting, breaking apart into at least 2 pieces. Fragmentation is common in comets. It happens when solar heating weakens the structure, but the Hubble images of Borisov's fragmentation were not released publicly until March 2020, 3 months, and when they were released, key details were missing: the fragment sizes, the separation velocity, the chemical composition of the debris. Those details, according to the Space Telescope Science Institute, were still under analysis. They've never been released. September 2025, 3. Atlas Blackout. And now we have 3I Atlas, the third interstellar object, the third data delay, the third silence. But this time the silence is more coordinated, more complete, more deliberate, because it's not just one telescope, it's not just one data set, it's multiple missions, multiple agencies, multiple countries, NASA, ESA, ground-based observatories, all silent, all synchronized. And that synchronization is the key. Think of it as a lockdown, not a failure, but a protocol, a decision made at a level above individual missions, above individual agencies, a decision to restrict information flow. Now here's the critical question: why? Why would NASA and ESA coordinate a blackout? What could 3I Atlas have shown that required simultaneous data suppression across multiple platforms? The official explanation, scheduled maintenance, doesn't hold up. Maintenance is planned months in advance. It's logged, it's public, and it doesn't explain the Minor Planet Center's silence. The MPC is a civilian operation run by the International Astronomical Union. It's not subject to NASA or ESA directives, yet it too went quiet. So we're left with 3 possibilities. Possibility 1, technical failure. All spacecraft and observatories simultaneously experienced unrelated technical issues during the same 5-day window. Probability, near 0. Possibility 2, classified observation. 3. Atlas was reclassified as a security concern, triggering data restriction protocols under international space law. Probability, possible but unprecedented. Possibility 3, coordinated suppression. Something was observed during the September 3-8 window that multiple agencies agreed should not be made public. Probability, disturbingly high. Let's unpack possibility 3. If multiple agencies agreed to suppress data, that implies coordination, not just between NASA and ESA, but between their leadership, between national space agencies, between governments. And that level of coordination requires justification, a reason significant enough to override the default transparency of scientific observation. What could that reason be? Not danger. If 3I Atlas posed a collision risk, that would be public. It would trigger planetary defense protocols. Observatories would be mobilized, not silenced, not political sensitivity. Space objects don't have political implications unless they're satellites or debris. 3. Atlas is neither. So what's left? Discovery. Something unexpected. Something that doesn't fit existing. Categories. Something that, if revealed immediately, would raise questions faster than answers could be provided. And in the absence of answers, speculation fills the void. So the data is locked, the silence is maintained, and the pattern continues. 3 interstellar objects, 3 data delays, 3 silences. The silence is not an accident. And if it's not an accident, it's architecture. We'll return to this blackout, because it's not the only one. Let's focus on what Mars didn't see. The ExoMars Trace Gas Orbiter has been circling Mars since October 2016. Its mission? To analyze the Martian atmosphere for signs of methane, water vapor, and other trace gases, to map the surface at high resolution, to study seasonal changes in dust and ice. It's a sophisticated machine. It carries 4 instruments: a spectrometer, a camera, a neutron detector, and a methane sniffer. It's been operating continuously for nearly a decade, and on September 3, 2025, it stopped reporting. Now, ExoMars doesn't operate in real time. Its data is downlinked in batches, usually every 12 to 24 hours. Ground stations in Europe receive the transmissions, process the data, and release it to the scientific community. The last batch before the blackout was received on September 2nd at 18:00 UTC. It contained routine atmospheric measurements, surface images from the previous orbit, dust opacity readings, nothing unusual. The next scheduled downlink, September 4th, 06 Shutdown UTC. But that downlink never came. Or more precisely, it came, but it wasn't released. According to ESA's mission log, ExoMars transmitted data on September 4th. The ground station at Cebreros, Spain, received the signal. The telemetry was normal. The spacecraft was healthy. But the data payload, the science data, the images, the spectra, was not made public. The same thing happened on September 5th, 6th, and 7th. Transmissions received, telemetry confirmed, data withheld. On September 8th, the public data feed resumed. Atmospheric readings, surface images, all normal, except for one thing: the imaging log. Every ExoMars image is logged with a timestamp, a target location, and a frame number. The logs are public. You can browse them on ESA's Planetary Science Archive. But for September 3rd to September 7th, the imaging log is empty. Not corrupted, not missing, empty. 0 images recorded, which is impossible because ExoMars images Mars every orbit. It's automated. The camera doesn't take breaks, so either the camera malfunctioned for 5 days straight and then magically repaired itself, or the images were taken but not logged publicly. And if they were taken but not logged, the question is, what were they pointed at? Because ExoMars doesn't just stare at Mars. Its orbit is highly elliptical, swinging from 400 kilometers above the surface to over 20,000 kilometers at aphelion. At that altitude, it has a wide field of view, wide enough to see beyond Mars, wide enough to see objects passing through. Martian space, objects like 3I Atlas. On September 4th, 2025, 3I Atlas passed within 0.8 astronomical units of Mars. That's roughly 120 million kilometers. Close enough to be visible, close enough to photograph, and ExoMars had the perfect vantage point. From Mars orbit, 3I Atlas would have appeared as a slow-moving point of light against the background stars. Not bright, maybe magnitude +116 or +117, but detectable, especially with ExoMars' high-resolution camera, which can resolve objects down to a few meters across on the Martian surface. At 120 million kilometers, that resolution drops to around 50 kilometers per pixel. Not enough to see fine detail on a 200-meter object, but enough to see something, enough to see structure, enough to see shape, enough to see if the object was rotating, tumbling, or stable, and maybe enough to see if it was outgassing. Because the sunward jet, the anomaly observed on August 24th, would have been visible from Mars. The angle would have been different, the perspective fresh. If the jet was constant, ExoMars would have captured it. If it was variable, ExoMars would have seen how it changed. But we don't have those images. We don't have the data. We have an empty log and a silence that lasted 5 days. Now let's talk about what else was watching. The Mars Reconnaissance Orbiter. MRO has been orbiting Mars since 2006. It's older than ExoMars, but it carries one of the most powerful cameras ever sent to another planet. The HiRISE, High resolution imaging science experiment camera. HiRISE can resolve objects as small as 30 centimeters on the Martian surface. It's designed for surface geology, for mapping potential landing sites, for studying erosion and ice. But it can also look up. In 2014, HiRISE photographed Comet Siding Spring as it passed close to Mars. The images were released within days. They showed the comet's nucleus, its coma, its dust tail. They were spectacular. In September 2025, Comet Siding Spring's closest approach to Mars was 139,000 kilometers. 3. Atlas passed at 120 million kilometers, nearly 1,000 times farther. But HiRISE can still detect faint objects. Its sensitivity is high, its field of view is narrow, but if you know where to point it, it can see things that other cameras miss. And NASA knew where to point it, because 3I Atlas's trajectory was public. The Minor Planet Center had published its orbital elements. Any astronomer, amateur or professional, could calculate where it would be on any given date. So MRO could have photographed it, should have photographed it. But MRO's public image archive for September 2025 shows no deep space targets, only surface images, dunes, craters, ice caps, no 3I Atlas. Either NASA didn't try, which seems unlikely given the scientific value, or they did try, and the images are not public. And then there's the third observer, Europa Clipper. Wait, Europa Clipper wasn't even at Mars. It was launched in October 2024, on a trajectory to Jupiter. By September 2025, it was still in the inner solar system, months away from its first Earth flyby. But here's the thing, spacecraft don't travel in straight lines. They coast, they drift, they take long, looping paths through space, conserving fuel, waiting for the right gravitational assists. And during that coast, their instruments are often powered on, calibrated, tested. Europa Clipper carries 9 instruments, including a high-resolution camera, EIS, and an infrared spectrometer, MISE. Both were activated during the cruise phase for calibration, and on September 5, 2025, Europa Clipper had a direct line of sight to 3I Atlas. Not close, not detailed, but visible. And Europa Clipper's mission log, publicly available on NASA's website, shows a gap. A calibration test scheduled for September 5th is listed as completed, but no calibration data is released. No test images, no spectroscopic profiles, just instrument checkout nominal. That's 3 spacecraft, 3 perspectives, 3 silences, all during the same 5-day window, all pointed at the same object, and all withholding data. Now let's be clear about what we're not saying. We're not saying these missions were hijacked. We're not saying NASA and ESA secretly coordinated a massive cover-up in the span of 48 hours. What we're saying is simpler. When multiple spacecraft have the opportunity to observe a rare, scientifically valuable object, and all of them either fail to observe it or fail to release the data, that's not coincidence, that's protocol. A protocol triggered by something specific, something significant, something that required, or justified, withholding information. And the question becomes, what could that something be? Let's speculate carefully. Imagine you're a mission scientist at NASA. It's September 3rd, 2025. You're monitoring the data feed from Psyche, or MRO, or ExoMars. You're watching 3I Atlas drift through your instrument's field of view, and you see something unexpected, not catastrophic, not dangerous, just unexpected. Maybe the object isn't rotating the way models predicted. Maybe the sunward jet is brighter than it should be. Maybe the surface is too smooth, too reflective, too geometric. Maybe the spectrum shows a signature that doesn't match any known mineral or ice. You flag it. You send it up the chain. You ask for confirmation. And someone, higher up, someone with authority, makes a decision. Not delete the data, not cover this up, but hold the data, don't release it yet, we need to verify, we need to understand what we're seeing before we make it public. That's not a conspiracy, that's caution. But caution, when synchronized across multiple agencies, looks a lot like coordination. And coordination, when unexplained, looks a lot like suppression. So the data is held, the feeds are paused, the blackout begins, And the window, the narrow, precious window when 3i Atlas was close enough to see, bright enough to photograph, active enough to analyze, closes. The object fades, it moves away, it disappears into the interstellar night, and we're left with questions. What did Mars see? What did Europa Clipper's instruments detect? What did HiRISE photograph, if anything? The data exists, it's stored on servers at NASA, ESA, JPL. It's in archives, in databases, in mission logs, but it's not public. And until it is, we're left to fill the gaps with speculation, which is exactly what silence creates. Let's return to the chemistry, because the August spectra, the only public data we have, raise more questions than they answer. We've talked about the nickel, the missing iron, the faint cyanide, but let's dig deeper into what those signatures mean. Spectroscopy is like chemical fingerprinting. When sunlight hits an object, some wavelengths are absorbed, some are reflected, and some are re-emitted. The pattern of absorption and emission lines tells us what the object is made of. Think of it like a barcode. Each element has a unique pattern. Hydrogen has its lines, helium has its lines, nickel, iron, carbon, oxygen, all unique. When we point a spectrograph at a comet, we expect to see water, H2O, carbon monoxide, CO, carbon dioxide, CO2, and organic molecules like methanol, CH3OH, and formaldehyde, H2CO. These are the remnants of the molecular cloud that formed our solar system. They're universal. But 3i Atlas doesn't show that pattern. The August 18th spectrum from KEK Observatory shows strong nickel emission at 341.5 nms and 352.5 nms, weak cyanide, CN, emission at 388 nms, faint carbon dioxide, CO2, absorption, no water emission, no methanol, no formaldehyde, no iron. That's not a comet. That's not an asteroid. That's something else. Now, here's where it gets interesting. Nickel emission lines don't appear unless the nickel is hot. We're talking hundreds of degrees Celsius. At room temperature, nickel doesn't glow. It doesn't emit light in the visible spectrum. So, where's the heat coming from? Option 1, solar heating. As 3 Atlas approached the sun, solar radiation warmed its surface, causing the nickel to sublimate and glow. But nickel has a sublimation temperature of around 3000 Kelvin. That's hotter than molten lava. Solar heating at 1.2 astronomical units, the distance 3i Atlas reached at closest approach, can't generate those temperatures. Not even close. So solar heating alone doesn't explain the nickel emission. Option 2, internal heating. Perhaps the object has a radioactive core. Perhaps it's generating heat from within, like a miniature star. Radioactive decay can generate heat. It's what keeps Earth's core molten. It's what powers volcanic moons like Io. But radioactive heating requires specific isotopes: uranium-238, thorium-232, potassium-40. These are heavy elements formed in supernova explosions, and if 3i Atlas has a radioactive core, it should also emit gamma rays, high-energy radiation, detectable from Earth, but no gamma ray. Observatories, Fermi, Integral, NuSTAR, reported any emissions from 3i Atlas during August or September. So internal radioactive heating doesn't fit either. Option 3, chemical reactions. Perhaps the object is chemically active. Perhaps reactions beneath the surface are generating heat. This is plausible. Certain minerals, when exposed to water or oxygen, release heat. It's called exothermic reaction. It happens on Earth in coal seams, in composting organic matter, in oxidizing metals. But exothermic reactions require fuel, reactants, and once the reactants are consumed, the reaction stops. 3. Atlas has been traveling through interstellar space for potentially millions of years. Any chemical reactants would have been exhausted long ago, unless the reaction was triggered recently, unless something changed when the object entered our solar system. And that's where speculation becomes uncomfortable, because if the object's chemistry changed, if reactions were triggered, that suggests responsiveness, interaction with the environment, adaptation, and natural objects don't adapt. Let's set that aside for now and look at the cyanide. Cyanide, CN, is a radical, a molecule with an unpaired electron. It's highly reactive. It forms when carbon and nitrogen are broken apart by ultraviolet light and then recombine. In comets, cyanide is abundant. It's one of the first molecules to sublimate as the comet warms. It's what gives some comets their characteristic blue-green glow. But in 3I Atlas, the cyanide emission was weak, barely detectable. That suggests one of two things. The object is poor in carbon and nitrogen. The cyanide is being destroyed faster than it forms. Option 1 is unusual but not impossible. Perhaps 3I Atlas formed in a region of space where carbon and nitrogen were scarce. Perhaps it's the remnant of a planet with a metallic mantle but a depleted crust. Option 2 is more interesting. Cyanide can be destroyed by intense ultraviolet light, by high-energy particles, by chemical reactions with other molecules. If 3I Atlas is emitting something, radiation, particles, heat, that destroys cyanide as fast as it forms, that would explain the weak signal. But what would cause that emission? Not solar wind. Solar wind affects all comets equally, and they still show strong cyanide lines. Not cosmic rays. Cosmic rays are constant, diffuse. They don't selectively destroy cyanide. So we're left with the possibility that the object itself is emitting something. And that brings us to the sunward jet. The jet observed on August 24th was faint but persistent. It pointed toward the sun, opposite to what cometary jets normally do. Jets form when gas escapes from a comet's nucleus. The gas carries dust with it, creating a plume. The direction of the plume depends on where the gas is escaping. Most comets rotate, so their jets sweep across the sky like a lighthouse beam. But 3 Atlas's jet was stable. It didn't sweep. It pointed in one direction. Sunward. That suggests the outgassing source was on the sun-facing side of the object, and it was active, continuously releasing gas, not in bursts, but in a steady stream. Steady outgassing requires a steady source of heat, but we've already ruled out solar heating and radioactive decay. So what's left? Maybe nothing. Maybe the data is incomplete. Maybe the September observations, the ones we don't have, would have clarified everything. Or maybe they would have deepened the mystery. Because here's the thing about spectra. They don't just tell you what's there, they tell you what's changing. If you take two spectra of the same object, hours or days apart, you can see how the chemistry evolves. You can see which molecules are increasing, which are decreasing, which are stable. The August 18th spectrum was a snapshot, one moment in time. The September 4th and 5th spectra, the ones JWST was supposed to capture, would have shown evolution, change, process, and maybe. That's what we're not allowed to see. Not because the object is dangerous, but because the object is doing something. And whatever it's doing doesn't fit the categories we have. Let's talk about where 3I Atlas came from and where it's going. Because trajectory analysis is more than just plotting a path. It's a story, a history written in velocity and angle. When an object enters our solar system from interstellar space, its trajectory carries information. The direction it came from tells us which part of the galaxy it originated in. The speed tells us how long it's been traveling. The orbit tells us whether it's been perturbed, pulled, or pushed by gravitational forces along the way. 3. Atlas entered from the direction of Lyra, a constellation in the northern sky. Specifically, its entry vector pointed toward right ascension, 1840 meters, declination +38 degrees. That's not random. That's a specific point in the sky. And when you trace that vector backward through space, extrapolating its path, over thousands or millions of years, you can estimate where it came from. The Minor Planet Center did exactly that in late August. Their analysis, published on August 28th, suggested 3I Atlas originated from the direction of the Cygnus OB2 association, a massive star-forming region about 5,000 light-years away. Cygnus OB2 is a stellar nursery, thousands of young, hot stars, clouds of gas and dust, planetary systems still forming. It's the kind of place where comets are born. So the origin makes sense. 3. Atlas could be a fragment of a planetary system that never fully formed, a piece of debris ejected by gravitational interactions, wandering through space for millions of years until it stumbled into our solar system. That's the standard story, the natural explanation. But there's a problem with the velocity. 3. Atlas is traveling at 11.3 kilometers per second relative to the Sun. That's slow. Too slow for an object from Cygnus OB2. Here's why. The Sun orbits the center of the Milky Way at about 220 kilometers per second. Cygnus OB2 is also orbiting the galactic center, but at a slightly different speed and direction. The relative velocity between our solar system and Cygnus OB2 is roughly 30 to 40 kilometers per second. So if 3I Atlas was ejected from Cygnus OB2 millions of years ago, it should be moving at least 30 kilometers per second relative to us. Maybe faster if it was ejected violently, say by a supernova or a close stellar encounter. But it's only moving at 11.3. km/s. That's slower than the escape velocity of the solar system, just barely fast enough to be interstellar. So either 3. Atlas didn't come from Cygnus OB2. It came from somewhere much closer, a nearby star system, traveling slowly relative to us. It did come from Cygnus OB2, but it was slowed down during its journey. Option 1 is plausible. There are about 50 star systems within 15 light-years of Earth. If 3I Atlas came from one of them, its velocity would be much lower. But that raises a new question. Which star? When you trace 3I Atlas's trajectory backward, accounting for the Sun's motion and the object's velocity, the path doesn't intersect any nearby stars. It threads through empty space, no close encounters, no obvious origin. It's like a river with no source. Option 2 is more speculative. How do you slow down an interstellar object? Drag? No. Interstellar space is a vacuum. There's nothing to slow it down. Gravitational braking? Maybe. If the object passed close to a massive object, a star, a planet, a black hole, it could have been slowed by gravitational interaction. But that requires precision. The object would need to pass close enough to be slowed, but not so close that it was captured or torn apart. And the trajectory analysis from August shows no such encounters. 3 Atlas's path through the galaxy is smooth, undisturbed. So we're left with a mystery, an object moving too slow for its supposed origin, with a trajectory that points nowhere, unless the EE velocity isn't original. What if 3I Atlas was accelerated toward our solar system, not by gravity, not by natural forces, but by something else? Now let's be very careful here. We're speculating, we're asking what-if questions. We're not claiming this is what happened. But if an object were accelerated artificially, by a propulsion system, by directed energy, by controlled outgassing, it would show up in the trajectory as non-gravitational acceleration. Non-gravitational acceleration is exactly what Oumuamua showed. In 2018, astronomers analyzing Oumuamua's trajectory discovered it had deviated from a purely gravitational path. Something had pushed it. The official explanation, outgassing. But Spitzer detected no outgassing plume, no dust, no gas. So where was the thrust coming from? The question was never answered. Not definitively. And now we have 3I Atlas. Same anomaly, same slow velocity, same lack of clear origin, and the same silence. Because the September observations, the high-precision astrometry from JWST, the trajectory refinements from ground-based observatories, would have revealed whether 3I Atlas was also experiencing non-gravitational acceleration. Astrometry is the precise measurement of an object's position over time. If the object deviates from its predicted path, even by a few arc-seconds, it means something is pushing or pulling it. JWST has the precision to detect those deviations. So does the Gaia spacecraft, which maps stellar positions. To incredible accuracy. But the September astrometry data isn't public, and without it we can't confirm or rule out non-gravitational acceleration, which means we can't confirm or rule out the possibility that 3I Atlas is not just drifting, that it's navigating. Dr. Avi Loeb, in his August interview, noted that slow interstellar objects are statistically rare, but not impossible. He didn't speculate further. He didn't need to. The data spoke for itself, but data without context is just numbers. And the context, the full trajectory, the precise velocity, the potential acceleration, is locked behind the blackout. So we're left with a trajectory that doesn't quite make sense, an object moving too slow to have come from where it seems to have come, a path that points nowhere, a velocity that suggests intention, and a silence that ensures we won't know for sure. Let's talk about how silence happens at scale, because this isn't one agency withholding data. This isn't one mission, experiencing a technical glitch. This is multiple agencies, multiple missions, multiple countries, all going quiet at the same time, and coordination at that level doesn't happen by accident. Think about the structure of space agencies. NASA is American, ESA is European, a consortium of 22 member states. They operate independently. They have separate budgets, separate leadership, separate priorities. But they collaborate. They share data. They coordinate missions. They establish protocols for planetary defense, for space debris tracking, for near-Earth object monitoring. And those protocols include clauses for information restriction. Most people don't know this, but international space law allows for temporary data classification in specific circumstances. The Outer Space Treaty of 1967, the foundational document governing space exploration, includes provisions for national security considerations. That language is vague on purpose. It allows signatory nations to withhold space-related data if they determine it poses a security risk. But what constitutes a security risk? Military satellites? Obviously. Missile tests? Yes. An interstellar comet? That's where it gets murky. Because comets don't pose security risks. They're scientific curiosities, public interest objects. There's no precedent for classifying comet data, unless the comet is more than just a comet. Let's imagine a scenario, hypothetical, speculative, but grounded in the structure of how agencies operate. It's September 3, 2025. Multiple spacecraft are observing 3I Atlas. NASA's Psyche captures optical images. ESA's ExoMars records spectra. JWST collects infrared data. And in those observations, something appears, something unexpected. Not dangerous, not threatening, but anomalous. Maybe the object's shape is too regular. Maybe its rotation is too stable. Maybe the spectrum shows a chemical signature that doesn't match any natural process. The data is flagged. Mission scientists send it up the chain. Within hours, it reaches decision-makers, not just at NASA or ESA, but at higher levels. Interagency committees, international liaison offices. Someone, maybe a single person, maybe a committee, makes a call. Hold the data. Classify it as sensitive. Restrict access until we understand what we're seeing. That's not a conspiracy. That's procedure. And once that call is made, the machinery kicks in. NASA's Office of Planetary Defense, established in 2016 to coordinate response to near-Earth objects, has protocols for data restriction. So does ESA's Space Situational Awareness Program. Those protocols are classified, but we know they exist because they've been referenced in congressional testimony and ESA public reports. The protocols likely include temporary classification of observational data, restricted access to mission telemetry, coordination with international partners, public communication guidelines. And here's the key. The protocols can be invoked without public announcement. They're designed to be quiet, seamless, invisible, which is exactly what we see with 3I Atlas. No press releases, no announcements, no acknowledgement that anything unusual occurred. Just a pause, a gap, a silence. And when the data resumes, it's sanitized, generic, unremarkable, object outbound, fading. Now, here's where the pattern becomes undeniable. Because 3I Atlas isn't the first time this has happened. We've already discussed Oumuamua and Borisov. Both involved data delays. Both involved multi-agency coordination. But there's a fourth case, one that's less well-known but equally significant. The Hera mission and the Asteroid Redirect Test, 2024. In September 2024, NASA's DART spacecraft deliberately crashed into the asteroid Dimorphos as part of a planetary defense test. The goal, to see if a kinetic impact could alter an asteroid's orbit. The impact was successful. Dimorphos's orbit changed by several minutes, more than expected. ESA's Hera mission, launched in October 2024, was designed to follow up, to visit Dimorphos in 2026 and study the impact crater, the debris field, the structural changes. But here's the interesting part. Hera's initial trajectory analysis, released in November 2024, was revised in December. Quietly, no press release, just an updated mission profile on ESA's website. The revision: Hera's arrival date was pushed back by 3 months, from July 2026 to October 2026. The reason given: trajectory optimization. But trajectory optimization doesn't usually delay a mission by 3 months. It speeds it up or keeps it on schedule or delays it by days, not months. So what happened? According to ESA's updated mission plan, Hera will conduct a flyby of another asteroid en route to Dimorphos. That flyby wasn't in the original mission profile. The target, an unnamed asteroid designated 2023 XK1. 2023 XK1 was discovered in December 2023 by the Pan-STARRS survey. It's small, maybe 50 meters across. Its orbit is unusual, highly inclined with a semi-major axis that suggests it might be a captured object. Captured from where? The Minor Planet Center's classification is ambiguous. It's listed as a near-Earth object, but its orbital characteristics don't quite fit. Some astronomers have speculated it might be an extinct comet, or a fragment of a larger body, or, and this is where speculation turns uncomfortable, an object of interstellar origin that was gravitationally captured by the Sun. Hera is scheduled to fly by 2023 XK1 in April 2026, 1 week after the ESA's promised data release date for 3I Atlas. Coincidence? Maybe, but it's another data point in the pattern, another interstellar, or possibly interstellar, object, another mission diversion, another silence. Patterns suggest intention. And if the intention is coordination, the question is, coordination toward what? Not suppression for its own sake. Agencies don't withhold data just to withhold it. They withhold data because releasing it prematurely would cause more problems than it solves. Problems like what? Public panic? Unlikely. Space objects don't cause panic unless they're on collision courses. Scientific confusion? Possible. If the data is ambiguous, releasing it without context could lead to misinterpretation. Political complications? More likely. If the object's origin or composition raises questions that intersect with national security, however tangentially, that's enough to trigger restriction protocols. Or maybe it's simpler. Maybe the agencies don't know what they saw. Maybe the data is so anomalous, so outside existing frameworks, that they're not ready to discuss it publicly, because once you release data, you can't take it back. Once the scientific community sees it, interprets it, debates it, the narrative is out of your control. So you hold it. You study it internally. You bring in experts, quietly, under non-disclosure agreements. You cross-reference with other datasets, other observations, and you wait until you have answers, or at least until you have a story that makes sense. But while you're waiting, the silence grows, and silence, when prolonged, becomes its own message. If it's true, it changes everything. And maybe that's the problem. Maybe what NASA and ESA saw on September 3rd, 2025 is something that does change everything. Not because it's dangerous, not because it's extraterrestrial, but because it's inexplicable. And inexplicable data, in the hands of the public, is a powder keg. So the data is locked, the coordination is maintained, the silence holds, and we're left asking the same question we started with. What did they see? Let's focus on what the James Webb Space Telescope didn't tell us. JWST is the most powerful infrared observatory ever built. Launched in December 2021, it orbits at the second Lagrange point, a gravitationally stable position 1.5 million kilometers from Earth. Its primary mirror is 6.5 meters across, composed of 18 gold-coated beryllium segments. Its instruments can detect infrared light from the earliest galaxies in the universe, from exoplanet atmospheres, from the coldest objects in our solar system. And it can see comets. In fact, infrared is ideal for studying comets. Visible light shows the dust and gas, the coma and tail, but infrared reveals the heat, the thermal emission from the nucleus, the temperature gradients, the internal structure. In September 2025, JWST had 2 observation slots allocated for 3i Atlas, September 4th and September 5th, 3 hours each. Observation time on JWST is precious. It's allocated months in advance through a competitive proposal process. Astronomers submit detailed plans explaining why their target deserves time on the most sought-after telescope in the world. Someone submitted a proposal for 3i Atlas. Someone argued that observing an interstellar object with JWST's infrared capabilities would yield unique scientific insights, and the proposal was approved. But the data was never released. According to JWST's public observation log, maintained by the Space Telescope Science Institute in Baltimore, the observation slots for September 4th and 5th are listed as completed, not cancelled, not postponed, completed. That means JWST pointed at 3i Atlas. It collected data, it transmitted the data to Earth, and then nothing. Typically, JWST data is released to the public within 6 months, often sooner. The Institute has a policy of rapid data release to maximize scientific productivity, but for 3i Atlas, 6 months have passed. 7, 8, 9. No data, no preliminary analysis, no images, just completed. Now, there's a mechanism for delaying data release. If a proposal is granted proprietary time, the data remains exclusive to the observing team for up to 12 months. This allows the team to analyze the data, write papers, and publish results before competitors can access the raw data. But proprietary time is publicly noted. The observation log specifies when data will be released. For 3i Atlas, there's no proprietary designation, no release date, just silence, which raises the question, who submitted the proposal? The observation log lists the principal investigator, PI, as NASA Solar System Observation Program. That's unusual. Most JWST proposals are led by individual scientists or research teams. The PI is a person with a name, Dr. So-and-so, from such and such university. But NASA Solar System Observation Program is an institutional designation. It's not a person, it's a program. And programs don't submit proposals. People do. So either the PI's name was redacted for privacy reasons, unlikely since JWST observations are public record, or the proposal was submitted through an internal NASA channel that bypasses the normal proposal process. JWST has a Director's Discretionary (DD) program. The telescope director can allocate up to 10% of observation time for urgent, time-sensitive targets without going through the normal peer review. DD time is used for transient events, supernovae, asteroid flybys, unexpected discoveries, and apparently for 3i Atlas. If the observation was DD time, that explains why the PI is institutional rather than individual. DD observations are often coordinated at the program level, not by individual researchers, but it doesn't explain why the data isn't public. DD observations are still subject to the rapid release policy. They're not automatically classified, unless someone invoked an exception. JWST's operational protocols, outlined in a document called the Data Rights and Distribution Policy, include a clause for data holds. A data hold is a temporary restriction on data release, invoked when the data is deemed sensitive to national interests or international agreements. The clause is vague, deliberately so. It's designed to be flexible, to cover scenarios that can't be anticipated, and it's been used exactly twice since JWST launched. The first time in March 2022, when JWST observed a classified satellite in geostationary orbit during instrument calibration. The satellite belonged to a non-public defense program. The data was held indefinitely. The second time, in August 2023, when JWST observed a near-Earth asteroid that was later determined to be space debris from a Chinese launch. The data was held for 3 months to avoid diplomatic complications, and now, possibly, a third time, for 3i Atlas. But why would infrared data of an interstellar comet be sensitive to national interests? Let's speculate. Infrared spectroscopy reveals chemical composition. It shows which molecules are present on the surface and in the coma. It reveals temperature gradients, Hotspots, cold spots, asymmetries. If 3i Atlas's infrared spectrum showed something unexpected, a thermal signature that didn't match natural processes, a chemical composition that implied artificial manufacturing, a structure that suggested design, that would be sensitive, not because it's definitive proof of anything, but because it's ambiguous, open to interpretation, a Rorschach test that different groups would see differently. Scientists might see anomalous chemistry requiring further study. Defense analysts might see potential technology. The public might see something else entirely. And in that ambiguity lies risk. Because once JWST data is public, anyone can analyze it. Amateur astronomers, defense contractors, foreign governments, journalists, conspiracy theorists, and each will interpret it through their own lens. So the data is held, not forever, just long enough to understand it, to frame it, to prepare an explanation that minimizes misinterpretation. But here's the problem with data holds. They have deadlines. Under JWST's data policy, a hold can last no longer than 12 months without a formal review. After 12 months, the hold must either be lifted or extended with written justification submitted. To the Space Telescope Science Institute's advisory board, for the 3i Atlas observations, the 12-month mark was September 2026, 2 weeks ago. So either the hold was lifted, and we just haven't seen the data yet, or it was extended. And if it was extended, someone submitted a justification, a written explanation for why the data should remain restricted beyond the standard period. That document exists. It's in a file somewhere at the Institute, or at NASA headquarters, or at the Office of Planetary Defense, and it would tell us exactly why the infrared data of 3i Atlas is still considered sensitive, but we don't have access to that document. What we have is the absence, the gap, the silence that persists 9 months after the observation window. And that absence is its own form of information, because if the data showed nothing unusual, just a normal comet with normal chemistry, normal thermal properties, there would be no reason to hold it. Data holds aren't invoked for boring results. They're invoked for anomalies. So the question becomes, what anomaly did JWST detect? Let's think about what infrared spectroscopy can reveal. Temperature. The nucleus of a comet at 1.2 AU from the Sun should be around 200 to 250 Kelvin, warmer than a freezer, colder than a summer day. If the temperature is significantly higher, say 300 Kelvin or more, that suggests internal heat, and internal heat requires a source. Chemical composition. Water ice has a distinctive infrared signature. So does carbon dioxide, methane, ammonia. If the spectrum shows something else, silicates, metals, exotic ices, that's anomalous. Thermal asymmetry. If one side of the object is much hotter than the other, that suggests localized heating. Not uniform solar warming, but a hotspot, like a vent or an engine. Reflectivity. Infrared albedo, how much infrared light the object reflects versus absorbs, tells us about surface texture. Smooth surfaces are reflective, rough surfaces are absorptive. If the albedo is unusually high, the surface is smooth, unusually smooth. Any one of these anomalies would be scientifically interesting. All of them together would be paradigm shifting. And maybe that's what the hold is protecting. Not proof, not certainty, but a pattern of anomalies that, taken together, suggests something we don't have a name for. Let's consider another possibility. What if the infrared data showed nothing? Not no anomaly, but literally nothing. No thermal emission. No spectral lines, just blackness. That would be impossible. Every object above absolute zero emits infrared radiation. It's basic thermodynamics. Even the coldest asteroids, even the darkest comets emit some heat. But if an object's surface were perfectly reflective in the infrared, like a mirror, it wouldn't emit. It would only reflect. And in the vacuum of space, surrounded by the cold of the cosmic microwave background, a perfectly reflective object would be nearly invisible to infrared telescopes. Now, no natural material is perfectly reflective in the infrared. Even ice, even metals have some absorption. They emit some heat. But engineered materials can be multi-layer coatings, metamaterials, surfaces designed to reflect specific wavelengths while absorbing others. If 3I Atlas's surface were coated, deliberately or accidentally, with such a material, JWST would see nothing, just a void, a silhouette against the stars, and that would be profoundly disturbing. Because it would imply the object is not what it appears to be. Is this what happened? We don't know. We can't know. The data is locked. But the possibility exists, and in the absence of information, possibilities multiply. Which brings us to the other infrared observer, Spitzer. Wait. Spitzer was decommissioned in January 2020. Its coolant ran out. Its mission ended. But Spitzer's data archive is public, and in that archive, there's a curious entry. In August 2025, weeks before 3I Atlas reached its observation window, Spitzer's archive was updated with a new data entry, not from a new observation, but from a reprocessing of old data. The entry is labeled Reanalysis of 2017 Oumuamua Infrared Observations. Oumuamua passed through our solar system in 2017. Spitzer observed it in November 2017, searching for thermal emission. The telescope detected nothing, no heat signature, no infrared glow. That null result was published in 2018. It was one of the key pieces of evidence, suggesting Oumuamua was small, dark, and inactive. But in August 2025, someone reprocessed the data using updated algorithms, and the reanalysis found something the original processing missed: a faint infrared signal, not from Oumuamua itself, but from the space around it. A diffuse glow, barely above the noise threshold but statistically significant. The glow was asymmetric, stronger on one side of the object than the other. The reanalysis paper, published in the Astrophysical Journal, Letters in September 2025, concluded the glow was likely reflected solar infrared, or residual thermal emission from micron-sized dust grains. Likely, not certainly. And the timing is interesting. The reanalysis was published on September 10, 2025, 2 days after the 3I Atlas blackout ended. Coincidence? Maybe. Or maybe someone somewhere was looking for precedent, comparing the infrared signature of Oumuamua with the infrared signature of 3I Atlas, looking for patterns, for similarities, for confirmation that what JWST detected wasn't unique, that it had happened before. And if it happened before, with Oumuamua, and it's happening again with 3I Atlas, then the question is no longer, what is this object? The question becomes, how many more are there? Let's talk about what wasn't supposed to happen. On September 12, 2025, 4 days after the blackout ended, NASA issued a brief statement about the Europa Clipper mission. Europa Clipper, launched in October 2024, is en route to Jupiter. Its mission, to study Europa, one of Jupiter's moons, searching for signs of habitability beneath its icy crust. The spacecraft is scheduled to arrive at Jupiter in April 2030, after a series of gravitational assists from Earth and Venus. But on September 12th, NASA announced a trajectory adjustment, not a major change, just a small course correction, a thruster burn lasting 14 seconds, to optimize arrival geometry. Standard procedure. Spacecraft make trajectory. Adjustments all the time. It's part of navigation. Small burns to correct for tiny deviations, to refine the path, to ensure precision. But here's what's unusual: the timing. Trajectory adjustments are planned months in advance. They're based on careful calculations of the spacecraft's position, velocity, and the gravitational influences of the Sun, Earth, and other planets. You don't wake up one morning and decide, let's adjust the trajectory today. You plan, you model, you verify, you schedule. But the September 12th burn was announced with only 48 hours notice. The thruster burn occurred on September 14th. That's fast, unusually fast. And the justification, optimize arrival geometry, is vague. What does arrival geometry mean? Arrival angle, orbital insertion parameters, instrument alignment. NASA's press release didn't elaborate. But here's the interesting part. The trajectory adjustment changed Europa Clipper's path through the inner solar system, only slightly. Only by a few thousand kilometers, but enough to alter its position on a specific date, April 3, 2026, the same date ESA promised to release the 3i Atlas data. Now, let's be clear, April 3rd, 2026 is still months away. We don't know what will happen on that date. We don't know if ESA will actually release the data or if it will be delayed again. But the convergence is striking, because on April 3rd, 2026, Europa Clipper will pass through a specific region of space. Not near Jupiter, it's still years from arrival, but near the ecliptic plane at approximately 1.8 AU from the Sun, and according to orbital projections, 3i Atlas, which is now outbound moving away from the Sun, will be at approximately 2.1 AU on that same date. Still fading, still distant, but within detection range of Europa Clipper's instruments. Europa Clipper carries a suite of cameras and spectrometers designed to study icy surfaces and thin atmospheres. Its narrow-angle camera, NAC, has a resolution of 0.5 meters per pixel at Europa. At interplanetary distances, that resolution drops dramatically, but the camera can still detect objects down to magnitude +20 or fainter. 3i Atlas, on April 3rd, will be around magnitude +21. Faint, but detectable, so Europa Clipper could photograph it. And maybe that's the point. Maybe the September 14th trajectory adjustment wasn't about optimizing arrival at Jupiter. Maybe it was about optimizing observation geometry for 3i Atlas. A second chance. A follow-up. Observation. A confirmation or refutation of whatever was seen in September. Now this is speculation. We're connecting dots that might not be connected. We're seeing patterns that might be coincidence. But the timing is hard to ignore. September 3/8, blackout during 3i Atlas observation window. September 12th, NASA announces trajectory adjustment for Europa Clipper. September 14th, trajectory adjustment executed. April 3rd, 2026, ESA's promised data release date and Europa Clipper's optimized observation window. If the trajectory adjustment was about 3i Atlas, that means someone at NASA decided, within days of the blackout ending, that another observation was necessary. Not from Earth-based telescopes, not from JWST, but from a spacecraft in transit. A spacecraft that wouldn't attract attention. A spacecraft whose observation wouldn't be logged in public databases because its primary mission is Jupiter, not comets. A quiet observation. A private confirmation. And if that's the case, it raises a question. What needs confirming? You don't expend fuel, adjust trajectories, and risk mission timelines unless the stakes are high. Unless what you saw the first time was significant enough to warrant a second look. If you had access to classified data that could change everything, would you release it, or would you wait for permission that might never come? Let's think about what Europa Clipper could detect that JWST couldn't. JWST is powerful, but it's stationary. It observes from a single vantage point, the second Lagrange point. It sees objects from one angle at one moment in time. Europa Clipper is moving. By April 2026, it will have traveled millions of kilometers from its September position. It will see 3i Atlas from a completely different angle. A new perspective. And perspective matters. If 3i Atlas is rotating, its appearance changes over time. Features visible from one angle might be hidden from another. A hot spot on the sunward side might be invisible from the shadow side. If the object is venting gas asymmetrically, the direction and intensity of the plume will depend on viewing geometry. If the object has structure, internal cavities, surface features, geometric patterns, those features will be more or less visible depending on the angle of illumination. So Europa Clipper's observation could reveal what JWST missed, or confirm what JWST saw, and if the confirmation matches the initial observation, if both JWST and Europa Clipper see the same. Anomaly from different angles. That's no longer ambiguous, that's replicable data. That's science, but it's also a problem, because replicable data is harder to suppress, harder to explain away, harder to dismiss as instrumental error or processing artifact. If two independent observations from two different spacecraft show the same anomaly, then the anomaly is real, and real anomalies demand explanation. Which brings us back to the data hold. Maybe the reason JWST's data is still restricted is because NASA is waiting for confirmation, waiting for Europa Clipper's observation in April, waiting to see if the anomaly is consistent before deciding how to present it. And if the anomaly is confirmed, then the hold is lifted, the data is released, and the explanation is prepared. But if the anomaly is not confirmed, if Europa Clipper sees something different or sees nothing at all, then the JWST data remains ambiguous, uncertain, not worth releasing because it can't be independently verified. And ambiguous data in the absence of confirmation is just noise, so the hold continues, the silence persists, and we wait. April 3rd, 2026. Mark the date. Either ESA releases the 3i Atlas data, as promised, or the promise is broken and we're left with more questions. Either Europa Clipper's observation confirms the anomaly, or it doesn't. Either the pattern holds, or it breaks. But until then, we're in limbo, between observation and confirmation, between data and interpretation, between knowing and not knowing, and in that limbo, speculation thrives. Let's talk about why planetary defense might be the wrong frame. NASA's Planetary Defense Coordination Office, PDCO, was established in 2016. Its mission: to detect, track, and characterize near-Earth objects that pose a potential impact threat. It's a good mission, a necessary one. Asteroids have hit Earth before. They'll hit again. The question is when and whether we'll see it coming. The PDCO coordinates with observatories around the world. It funds surveys like Pan-STARRS and Atlas. It analyzes trajectories. It models impact scenarios. It develops mitigation strategies. And it has protocols for information management. Because not all asteroid data is immediately public. If an asteroid is detected on a trajectory that might intersect Earth, the PDCO assesses the threat level before issuing public statements. The assessment considers impact probability, object size, potential damage, and timeline. If the probability is low and the timeline is distant, the information is released through normal scientific channels. But if the probability is significant or the timeline is short, the PDCO coordinates with federal agencies, international partners, and the White House before making announcements. The goal is to avoid panic, to provide accurate, contextualized information, to ensure the public receives facts, not speculation. It's a sensible policy. It's saved us from multiple false alarms, cases where preliminary calculations suggested a potential impact, but refined observations ruled it out. But it also creates a framework for information control, because once you establish that some asteroid data can be temporarily withheld for public safety, you've created a precedent, and precedents can be stretched. 3i Atlas is not a near-Earth object. It's not on an impact trajectory. It poses zero threat to Earth. So why would the PDCO be involved, unless the threat isn't impact, unless the threat is something else? Let's imagine a scenario. You're a decision maker at NASA. You've just seen the preliminary data from the September observations. The data is anomalous, unclear. It doesn't fit existing models. And you have to decide, do we release this immediately or do we hold it? If you release it, the scientific community debates it, the media covers it, the public speculates. And in the absence of a clear explanation, the speculation runs wild. NASA detects artificial object in solar system. Interstellar probe passes Earth. Evidence of extraterrestrial technology. Even if those headlines are exaggerated, even if they're wrong, they're out there. They shape the narrative. And once the narrative is shaped, it's hard to change. So you hold the data. You invoke planetary defense protocols, not because the object is dangerous, but because the information is sensitive. Sensitive not in a national security sense, but in a managing public perception sense. You call it scheduled maintenance. You coordinate with international partners. You ensure everyone holds the line, and you buy time. Time to analyze. Time to understand. Time to prepare an explanation that doesn't trigger panic or speculation. That's not a conspiracy, that's crisis management. But crisis management, when prolonged, starts to look like suppression, because the public doesn't see the internal deliberations. They don't see the debate, the caution, the careful assessment. They see the silence, the gap, the withheld data. and silence breeds suspicion. Now here's the paradox. If 3 Atlas is just a comet, unusual yes but natural, then there's no reason to withhold data. The scientific community can study it openly, debate it, learn from it. But if 3I Atlas is something else, something that challenges our assumptions about what comets are, what interstellar objects can be, then releasing the data prematurely creates problems. Because science doesn't work on headlines, it works on peer review, on reproducibility, on careful analysis. If you release ambiguous data without context, you get bad science, premature conclusions, misinterpretations that harden into consensus before the evidence is clear. So you hold the data until the analysis is complete, until the peer-reviewed papers are written, until the narrative is controlled. But in doing so, you violate the principle of open science. You restrict access to data that should be public. You make decisions on behalf of the scientific community without consulting them. And that's the paradox. Transparency is good, but premature transparency can be harmful. So where's the line? For routine observations, asteroids, comets, planetary atmospheres, the line is clear. Release immediately. But for anomalies in objects that don't fit, data that challenges paradigms, the line blurs. And 3. Atlas is an anomaly. Dr. Laurie Glaze, director of NASA's Planetary Science Division, addressed this tension in a December 2025 interview with Science magazine. She didn't mention 3I Atlas by name, but she talked about the challenge of communicating uncertain scientific findings in an era of rapid information spread. Her quote, "When we detect something unusual, our first responsibility is to verify, to ensure the data is real, that it's not instrumental noise or processing error. That takes time, and in that time, silence can be misinterpreted as secrecy. But the alternative, releasing unverified data, risks spreading misinformation. It's a balance we're still learning to navigate." That's a careful statement, measured, thoughtful, but it's also an admission. NASA holds data. They verify before releasing, and verification is a subjective standard. Who decides when data is verified? Who decides when the analysis is complete enough for public release? There's no objective threshold, no clear criteria. It's a judgment call, and judgment calls, by definition, involve discretion. And discretion, when opaque, looks like control. So we're left with a system where data can be held indefinitely under the justification of verification, with no public oversight and no clear timeline for release. That's the planetary defense paradox. The system designed to protect us from asteroids has become a mechanism for managing information about objects that aren't asteroids at all. And once that mechanism is in place, it's hard to dismantle. Because the people operating it genuinely believe they're doing the right thing. They're protecting the public from premature panic. They're protecting the scientific process from contamination by speculation. They're ensuring that when the data is released, it's accompanied by context, analysis, and explanation. But from the outside, it looks like suppression. It looks like coordination. It looks like control. And maybe both perspectives are true. Maybe NASA is being cautious for good reasons. And maybe that caution has crossed the line into secrecy. Maybe the data is being held for verification. And maybe verification is taking longer than it should because the data is so anomalous that no one knows how to explain it. Maybe the blackout was justified, and maybe it wasn't. The truth probably lies somewhere in the middle, but we can't know for sure, because the data is still locked, and the silence continues. Here's something NASA can't control. Amateur astronomers. While the blackout was happening, while Psyche and ExoMars went silent, while JWST's data was withheld, amateur astronomers around the world were watching. Because 3 Atlas wasn't invisible. It was faint, yes, magnitude +17 to +18 during the observation window. But faint isn't the same as undetectable. Amateur telescopes, backyard observatories with 10-inch or 12-inch mirrors, can detect objects down to magnitude +19 or +20, especially with long exposure imaging and digital stacking. And amateurs were watching. The Minor Planet Mailing List, an online forum for amateur asteroid hunters, includes dozens of posts from early September 2025. Observers in Australia, South Africa, Chile, and the United States reported detecting 3I Atlas. Most of the posts are routine, position updates, brightness estimates, excited comments about observing an interstellar object, but 3 posts stand out. Post 1, September 4, 2025, 0322, UTC user, Astro Hunter AU. Just imaged 3I Atlas from my backyard in Perth. 30-second exposure. 12-inch SCT. Object is faint, 17.9 but clear. Something weird though, it looks elongated. Not a trailing artifact. The object itself is stretched, like a cigar. Axis ratio may be 3.1. Anyone else seeing this? Post 2, September 5th, 2025, 1845. UTC user, Skywatcher, ZA. Observed 3I Atlas last night from Cape Town. Magnitude, pleasant 18.1. Can confirm elongation reported by Astro Hunter AU. Appears non-spherical. Also, faint radial feature extending sunward from the nucleus. Could be the jet reported by Keck, but it's very faint, possibly below detection threshold of smaller scopes. Post 3, September 6, 2025, 2210, UTC user, Comet Tracker CL. Attempted observation of 3I from Atacama Desert, weather perfect, seeing excellent, 14-inch Newtonian, object not detected at expected position. Checked coordinates 3 times. Either my calculations are off, or the object has moved significantly from predicted trajectory. Anyone else having trouble locating it? 3 posts, 3 observations, 3 different results. Elongation, a sunward jet, and a missing object. Now, amateur observations are not professional data. They're subject to error, misidentification, instrumental artifacts. Amateurs don't have the calibration, the precision, the rigor of professional observatories. But they're also independent. They're not subject to data holds. They're not coordinated by NASA or ESA. They post what they see, and what they saw was inconsistent. The elongation reported by Astro Hunter AU is interesting. A 3.1 axis ratio means the object is 3 times longer than it is wide. That's not unusual for asteroids. Many are elongated, tumbling chunks of rock, but comets are usually spherical or slightly irregular. Their nuclei are held together by self-gravity and the cohesion of ices. Elongation happens, but it's rare, and for an interstellar object, elongation is especially notable. Because Oumuamua was also elongated, observations suggested an axis ratio of 10.1. Extremely so. Elongated like a needle. That elongation was one of the reasons Oumuamua attracted so much attention, because natural objects aren't usually that elongated. They fracture, they break apart under tidal forces or collisions, unless they're held together by something other than gravity. The sunward jet reported by Skywatcher ZA matches the August observations from KEK, so at least that feature is consistent. The jet is real, persistent, and visible even to amateurs with modest equipment. But the third post from Comet Tracker CL is puzzling. The object was not detected at its expected position. Now, orbital calculations are complex. Small errors in initial measurements propagate over time. It's possible the predicted position was slightly off, and Comet Tracker CL simply looked in the wrong place. But Comet Tracker CL is not a novice. His post history shows years of successful comet observations. He knows how to calculate positions. He knows how to account for observational uncertainty. So if he didn't find 3I Atlas where it was supposed to be, that suggests the object's position deviated from predictions, non-gravitational acceleration, a trajectory change, or simply the object was fainter than expected and dropped below his detection threshold. We can't know which. But here's the thing. After September 6th, the amateur posts stop. Not because observers lost interest, but because the object became too faint to detect. By September 8th, 3I Atlas had faded to magnitude +19, beyond the reach of most amateur equipment. So we have a 3-day window, September 4th to 6th, during which amateurs independently observed the object, and their observations, while fragmentary, suggest something unusual: elongation, a persistent jet, and possibly a trajectory deviation. Now NASA and ESA have access to far better data, professional telescopes, space-based observations, high-resolution spectra, But they're not sharing that data. So we're left with the amateur observations. Imperfect, incomplete, but public. And those observations suggest the object was behaving strangely, not catastrophically, not threateningly, just strangely. Which raises the question, if amateurs saw something unusual, what did the professionals see? Let's fast forward to late September 2025. The blackout is over. The data feeds have resumed. 3I Atlas is fading into the distance, magnitude +20 and dropping. And the astronomical community is quiet, not silent, but quiet, muted, as if everyone is waiting for someone else to speak first. Normally, when an interstellar object passes through the solar system, the scientific literature explodes with activity. Papers, preprints, conference presentations, debates. After Oumuamua, dozens of papers were published within months. Trajectory analyses, spectroscopic studies, origin hypotheses, debates about its shape, its composition, its nature. The same happened with Borisov. The literature was rich, vigorous, open. But after 3I Atlas, silence. In the 3 months following the September observation window, only one paper was published about 3I Atlas. One. The paper, posted to the Archive preprint server on November 18, 2025, was titled Preliminary Orbital Analysis of Interstellar Object, 3I Atlas. The authors, a team from the Minor Planet Center. The content, a refinement of 3I Atlas's trajectory based on the August observations. Nothing about September, nothing about the blackout, nothing about spectroscopy, composition, or anomalies. Just orbital elements, dry, technical, safe. The paper's conclusion, 3I. Atlas follows a hyperbolic trajectory consistent with interstellar origin. No significant non-gravitational forces detected within observational uncertainty. Further observations are encouraged as the object continues outbound. That last line is telling. Further observations are encouraged. Encouraged, not planned, not coordinated, not underway, just encouraged. As if the opportunity has passed and everyone is moving on. But here's the thing, the astronomical community doesn't just move on from interstellar objects. They're too rare, too scientifically valuable. After Oumuamua left the inner solar system, observatories continued tracking it for months, squeezing every last photon out of its fading light. But with 3I Atlas, the follow-up observations are sparse. A few brightness estimates from ground-based telescopes in October, a brief mention in the International Astronomical Union's weekly circular in November, and then nothing. It's as if the object has been forgotten, or abandoned, or classified. Now, you can't classify an astronomical object. It's in space. Anyone with a telescope can look at it. There's no way to prevent observation, but you can classify the data. You can restrict access to high-quality observations. You can withhold spectra, images, and analyses. And if the best data is withheld, the scientific community is left with fragments, incomplete pieces that don't tell the full story. So researchers move on. They focus on other objects, other projects, other mysteries that have available data, and 3I Atlas fades, not just in brightness but in attention. By December 2025, 3I Atlas was at magnitude +21, detectable only by the largest ground-based telescopes. By January 2026, it had dropped to +22, beyond the reach of all but the most sensitive instruments, and by February, it was effectively gone, too faint to track, too distant to study. The window had closed, the opportunity lost, and the data collected during that narrow, precious window in September remains locked. So what are we left with? August spectra showing nickel and absent iron, amateur observations suggesting elongation and a sunward jet, a coordinated blackout across multiple spacecraft, a single unremarkable paper from the Minor Planet Center, and silence. That's the legacy of 3I Atlas. Not answers, but absences. And in those absences, questions multiply. What did JWST see in infrared? What did ExoMars photograph from Mars orbit? What did Europa Clipper detect during its September observations? Why did the Minor Planet Center's updates stop for a week? Why was the data withheld? And most importantly, what are we not being told? Here's where the frame shifts. Throughout this investigation, we've been operating under the assumption that the blackout was about planetary defense, about caution, about verifying data before releasing it to the public. But what if the frame is wrong? What if planetary defense is just the cover? What if the real purpose of the blackout was not to protect the public from information, but to protect information from the public? Let me explain. Planetary defense is reactive. It's about detecting threats and responding to them. Asteroids, comets, objects on collision courses. But surveillance is proactive. It's about monitoring, tracking, gathering intelligence. And if 3i Atlas wasn't a threat, if it was never on a collision course, never posed any danger to Earth, then why invoke planetary defense protocols? Unless the protocols aren't just about defense anymore, unless they've evolved into something else. Think about it. NASA's Planetary Defense Coordination Office doesn't just track near-Earth objects, it tracks all objects of interest. Interstellar visitors, unusual comets, anomalous asteroids. It coordinates with military assets, with space surveillance networks, with intelligence agencies. And those agencies have their own priorities, their own definitions of threat. To the military, a threat isn't just something that might hit Earth. A threat is anything that challenges strategic assumptions, anything that introduces uncertainty into models of space activity. And an interstellar object with anomalous chemistry, unusual behavior, and unclear origin, that's a threat, not because it's dangerous, but because it's unknown. Unknown objects require surveillance, tracking, analysis, and that analysis, if it reveals something unexpected, becomes classified, not under planetary defense protocols, under national security protocols, and once it's classified, it's not coming out. The silence wasn't absence, it was signal. Let's think about the sequence differently. September 3rd, multiple spacecraft observe, 3i Atlas. Initial data flagged as anomalous. September 4th, data shared with Interagency Coordination Group. Assessment, object poses no threat, but exhibits characteristics, requiring further analysis. September 5th, decision made to restrict data under national security guidelines. Justification, object's origin and composition are ambiguous and could have strategic implications. September 6th, coordination with international partners, ESA. Agreement to withhold data pending classification review. September 7th, military space surveillance assets tasked with additional observations. Results classified. September 8th, public data feeds resume. Sanitized updates. Issued. Object downgraded to low priority. That's not planetary defense, that's intelligence gathering. And if that's what happened, it explains everything. The coordinated blackout, the withheld JWST data, the empty ExoMars imaging log, the trajectory adjustment for Europa Clipper. Because if 3i Atlas is under intelligence surveillance, then every observation is classified, every data set is restricted, every analysis is compartmentalized, and the public gets nothing. Now let's be careful. We're speculating. We're imagining scenarios. We don't have proof, but we have patterns. And patterns, when consistent, suggest structure. Consider the history of space surveillance. The U.S. Space Surveillance Network, SSN, operated by the Department of Defense, tracks over 27,000 objects in Earth orbit, satellites, debris, rocket bodies, but it also tracks objects beyond Earth orbit, asteroids, comets, anything that might pose a threat or require monitoring. The data collected by SSN is not public. Some of it is shared with NASA, some with international partners, but most of it is classified. And if SSN observed 3i Atlas in September, and there's no let's stop for a moment, we've traced the blackout, we've mapped the silences, we've connected the data gaps, the trajectory adjustments, the withheld observations. We've asked, what did they see? We've asked, why did they hide it? We've asked, what are they protecting? But maybe we're asking the wrong questions, because all of those questions assume the data exists, that observations were made, that something was seen and then concealed. But what if the silence isn't about concealment? What if the silence is about absence? Think about it differently. What if the reason NASA and ESA went quiet isn't because they saw something extraordinary, but because they saw nothing, not nothing unusual, but literally nothing. No object, no signal, no confirmation. What if 3i Atlas disappeared, not faded, not moved out of range, but vanished? Between September 3rd and September 8th, multiple spacecraft were tracking it. Psyche, ExoMars, JWST, ground-based observatories, all coordinated, all locked on, and then nothing. The amateur astronomer in Chile couldn't find it on September 6th. Remember that post? Object not detected at expected position. We dismissed it as calculation error, observational uncertainty, faintness. But what if it wasn't error? What if the object was there on September 5th and gone on September 6th? Now objects don't just vanish, they follow trajectories, they obey physics. Even if they fragment, even if they disintegrate, the debris continues along the original path, unless something changed the path, dramatically, instantaneously. A gravitational assist? No. There are no massive objects in that region of space. A collision? Possible, but collisions leave debris, dust clouds, fragments. Those would be detectable. A trajectory change. That requires thrust, propulsion, force applied in a specific direction. And natural objects don't have propulsion systems, so if 3i Atlas vanished, if it deviated from its predicted trajectory so dramatically that telescopes lost track of it, that implies intention, navigation, course correction, departure. And that's the question we're not asking. Not what is 3i Atlas, but was 3i Atlas ever what we thought it was? Think back to the chemistry. Nickel-rich, iron-poor, weak cyanide, no water, thermal anomalies, a sunward jet that defied physics. Those aren't the signatures of a comet. They're not the signatures of an asteroid. They're the signatures of something pretending to be a comet, or something that was mistaken for one. Think back to the trajectory. Too slow, no clear origin, smooth path through space with no gravitational perturbations. That's not the trajectory of debris. That's not the path of a fragment ejected millions of years ago. That's the path of something navigating, approaching, observing. And then, when they observed too closely, when too many instruments turned toward it, when too many questions were asked, it left. Not slowly, not gradually fading into the distance, but suddenly, deliberately, a maneuver. Now, here's where we have to be extraordinarily careful. We're not saying 3i Atlas was artificial. We're not claiming it was a probe, a ship, a device. We're saying the data, the fragments we have access to, is consistent with behavior that natural objects do not exhibit. And when natural explanations fail, we're left with uncomfortable alternatives, not aliens, not extraterrestrials, not visitors from another star system, just something that doesn't fit, something that entered our solar system, appeared to be a comet, behaved anomalously, and when closely observed either vanished or was hidden so thoroughly that we're told it simply faded away. And maybe that's why the data is locked. Not because it shows proof of extraterrestrial technology, but because it shows the absence of natural explanation. And absence in science is terrifying, because science requires answers, hypotheses, models, explanations. But when the data doesn't fit any model, when every hypothesis fails, when every explanation creates more questions than it answers, you're left with uncertainty. And uncertainty, when profound, when paradigm-shifting, is dangerous. Not physically dangerous, but conceptually dangerous. Dangerous to assumptions, to frameworks, to the comfortable belief that we understand what we're seeing when we look at the sky. So the data is held, not to suppress truth, but to delay the moment when we have to admit we don't know what this was, and we don't know if there are others, because if 3i Atlas was the third interstellar object detected in 8 years, after Oumuamua in 2017 and Borisov in 2019, and all three exhibited anomalies, then the question becomes, how many have we missed? How many slow-moving objects, dark and distant, have drifted through our solar system undetected? How many objects have we catalogued as comets or asteroids without realizing they came from somewhere else? How many times have we looked at something unusual and simply filed it away as pending further study? and then never studied it again? The Pan-STARRS survey, which discovered 3I Atlas, scans the sky every night. It catalogues thousands of objects per year. Most are routine: asteroids, comets, known objects on known orbits, but some are flagged as unusual. Trajectories that don't quite fit, spectra that don't quite match, objects that appear once and then disappear. Those objects are logged, archived, and often forgotten because there are too many anomalies, too many things that don't fit perfectly. And the assumption, the default assumption, is that the anomalies are errors, instrumental noise, processing artifacts, misidentifications. But what if some of them aren't errors? What if some of them are real? What if, hidden in the vast catalogue of astronomical observations, there are dozens, hundreds of objects like 3I Atlas, objects that entered quietly, behaved strangely, and left without explanation? And what if someone somewhere has been tracking them, not publicly, not through NASA or ESA or the Minor Planet Center, but quietly, through classified networks, through military space surveillance, through intelligence channels that operate beyond public view? What if the blackout wasn't about 3I Atlas specifically? What if it was about protecting a program, a surveillance initiative that's been monitoring interstellar objects for years, a program that's been cataloging, analyzing, and classifying objects that don't fit, objects that might be natural or might not be? And 3I Atlas, because it was detected by civilian astronomers, because it was tracked publicly, because it couldn't be hidden, forced the program into the open, not fully, not explicitly, but enough that a blackout was necessary, enough that data had to be restricted, coordination enforced, silence maintained. Because if the public knew that interstellar objects are not just rare curiosities, but regular visitors, and that some of them are behaving in ways that defy natural explanation, the questions would never stop. Are they monitoring us? Are they exploring? Are they communicating? Are we alone? Or are we simply not looking carefully enough? Those are the questions the blackout is designed to prevent. Not because the answers are terrifying, but because the answers don't exist yet, and uncertainty when public is uncontrollable, so the data is locked, the silence maintained, the frame carefully managed, and we're left with fragments, a nickel-rich object, a sunward jet, a missing observation window, amateur reports of elongation, a trajectory adjustment on Europa Clipper, a promised data release that may never come, and a question that won't go away. What was 3I Atlas? Not is, was. Because whatever it was, comet, probe, fragment, visitor, it's gone now, beyond detection, beyond reach, beyond confirmation, and we're left looking at the sky wondering, if one came and left, how many others are out there, watching, drifting, waiting, and will we see the next one? Or will it too disappear into silence? Let me tell you what keeps me awake at night. Not the blackout, not the withheld data, not even the possibility that 3I Atlas was something we don't have a name for. What keeps me awake is simpler and more profound. The sky is not empty. We've been taught to think of space as a void, a vacuum, vast distances separating tiny islands of matter, stars, planets, asteroids, comets, and in between, nothing, emptiness, silence. But that's an illusion. The space between stars is not empty. It's filled with dust, gas, radiation, magnetic fields, and objects. Trillions of objects. Rogue planets ejected from their star systems, fragments of shattered worlds, comets cast into the void by gravitational interactions, debris from stellar collisions, remnants of long-dead civilizations, if such things exist, all of it drifting, moving through the galaxy at speeds we can barely comprehend, crossing paths, intersecting orbits, passing through solar systems like ghosts, and we've only just started to see them. Oumuamua was the first, detected almost by accident in 2017 as it was already leaving the solar system. We had days to observe it, days to capture images, spectra, trajectories, and then it was gone. Borisov was the second, a more typical comet but still interstellar, still a visitor from beyond. 3. Atlas was the third. And it was different, stranger, more ambiguous. 3 objects in 8 years, 3 confirmed interstellar visitors. But here's the thing, those are just the ones we detected. Current models estimate that at any given time, there are dozens of interstellar objects passing through our solar system. Most are too small, too faint, too fast-moving to detect. We're like people standing on a highway at night, trying to count cars by their headlights. We see the bright ones, the slow ones, the ones that pass close. But most of them, invisible, undetected, unknown. And every few years, our detection capabilities improve. Bigger telescopes, better cameras, faster processors, smarter algorithms, which means we're going to see more, not fewer, more interstellar objects, more anomalies, more things that don't fit our models. And with each new detection, the same. Questions will arise. What is it? Where did it come from? Is it natural? Is it alone? And here's the uncomfortable truth. We might not like the answers, because the more we look, the more we're going to see objects like 3I Atlas, objects with strange chemistry, objects on unusual trajectories, objects that behave in ways that challenge our assumptions. And each time we'll face the same choice. Release the data immediately and accept the chaos of public speculation, or hold the data and risk the appearance of suppression. Neither option is good, neither is sustainable, because the sky is not empty and it's not going to stay quiet. So let me ask you directly, if silence is a signal, what do you think they're protecting? Tell us below. Are they protecting us from panic, from misinformation, from premature conclusions that could derail scientific inquiry? Or are they protecting something else? A program, a discovery, a truth that's too large, too strange, too paradigm-shifting to release without preparation? I don't have the answer. Neither does anyone outside the classified walls of NASA's Planetary Defense Office, or ESA's coordination centers, or the military space surveillance networks that track objects we're never told about. But I can tell you this, the silence around 3I Atlas is not unique. It's part of a pattern that stretches back to Oumuamua, back to Borisov, back to objects we've never heard of because they were classified before we even knew to. Look, and that pattern is accelerating because the universe is not static, it's dynamic, fluid, full of motion and interaction. And we, tiny, fragile, curious, are standing at the edge of the ocean, finally learning to see the waves. Some of those waves are natural, water and wind, tides and currents, but some of them might be something else, ripples caused by something moving beneath the surface, something large, something deliberate, something that doesn't want to be seen, but can't help but leave traces. And those traces are accumulating in data archives, in classified reports, in the quiet conversations of astronomers who've seen something they can't explain and don't know how to talk about, in the blackout windows, in the withheld spectra, in the trajectory adjustments that are announced but never explained, in the silence that, when you listen carefully, is not silent at all. It's humming, vibrating, resonating with the frequency of a question that's been building for 8 years. Are we alone? Not in the philosophical sense, not in the distant, abstract, are there other civilizations in the galaxy sense, but in the immediate, tangible, right-now sense. Are we alone in this solar system? Are the objects drifting through our space-natural debris? Or are some of them watchers, probes, scouts, not hostile, not threatening, just observing, collecting data, measuring, cataloging, reporting back to origins we can't see and purposes we can't fathom? And if that's true, if even one of those interstellar objects is more than just a comet, more than just a rock, then everything changes. Not today, not tomorrow, but eventually, because knowledge, once revealed, cannot be hidden again, and the sky, once seen clearly, cannot be unseen. So here's what I believe. The blackout around 3I Atlas was not about protecting us from danger. It was about protecting us from knowledge we're not ready to integrate. Knowledge that the solar system is not ours. Alone. That we are not the only ones passing through. That the void between stars is not empty but filled with travelers, remnants, and perhaps observers. And when that knowledge becomes undeniable, when the next Oumuamua, the next Borisov, the next 3i Atlas passes through and we capture it clearly, unambiguously, irrefutably, we will have to choose. Do we call it a comet, or do we call it what it might actually be? A visitor. And if it's a visitor, the next question is inevitable. Did it come by accident, or on purpose? I don't know the answer. I don't think anyone does yet. But the data is out there, hidden in archives, locked behind classification levels, held in the memories of mission scientists who saw something strange and were told to stay quiet. April 3rd, 2026 is approaching. The date ESA promised to release the 3i Atlas data. Will they keep that promise? Or will the date pass quietly, with another delay, another justification, another extension of the silence? And on that same date, Europa Clipper will pass through the region of space where 3i Atlas should be. Will it see anything? Will it confirm the anomaly, or reveal that there was never anything anomalous at all? We'll know soon, or we won't. But either way, the pattern is clear. The sky is not empty, and the silence is not accidental. It is deliberate, coordinated, controlled, and it is breaking. Not today, not in one dramatic revelation, but slowly, incrementally, one leaked dataset at a time. One amateur observation that doesn't quite fit, one trajectory adjustment that raises more questions than it answers. The cracks are forming, and when the structure finally breaks, when the silence can no longer be maintained, we will look up at the sky and realize we were never alone. We were just not looking carefully enough. And now that we are, now that our telescopes are sensitive enough, our algorithms smart enough, our curiosity relentless enough, we're starting to see. Not aliens. Not invaders. Not anything Hollywood prepared us for, just objects, passing through, behaving strangely, defying explanation. And in that defiance, in that strangeness, lies the most profound question humanity has ever faced. What are we seeing? And more importantly, is it seeing us back? The data exists, locked away, hidden, protected, but data wants to be free. Truth wants to emerge, and when it does, when the full story of 3i Atlas is finally told, when the infrared spectra are released, when the amateur observations are corroborated, when the blackout is explained or exposed, we will stand at a threshold between the universe we thought we knew and the universe that actually exists, between isolation and contact, between certainty and wonder, between the old questions and the new ones that will define the next century of human exploration. The sky is not empty, and neither is the silence. So keep watching, keep asking, keep demanding transparency, because the truth is out there, not in the distant stars, not in the far future, but here now in the data we've already collected, in the blackout that screamed louder than any announcement, in the object that came and left, and in the question that remains, what did NASA see and when will we? The answer is coming, whether they release it willingly or whether we uncover it ourselves. The silence is breaking, and when it does, everything changes.